All right. Okay, let's go back to the Cobb-Doe plus UT function. If we want Q1 and Q2, Q1 and Q2, to satisfy some specific property like if we want Q1 to be good, Q2 to be good, what about alpha and beta? Should we restrict the range of the parameter? Alpha, beta, actually they are parameters. So parameter is actually 参数, okay? Parameter. So do we need to restrict the range of alpha and beta? So what does it mean if we say, oh, good one is a good, not bad, which means marginal utility 1 must be positive, right? The more good one we consume, the higher the utility we have, the happier we are, right? The more the better, right? So what is mu1? Partial u, partial q1, which would be alpha q1 to the power of alpha minus 1, q2 to the power of beta. And we want this to be positive. So we may conclude that, oh, alpha must be positive. Is that right? Okay? And so Q1 and U1. So if this is 0, then we require mu1 to fall within this area, right? This region, because mu1 must be positive. But it can be this or it can be this, mu1, or mu1. It's an increasing marginal utility, decreasing marginal utility, constant marginal utility. Okay? So the more we consume a good, all of them are positive, so they are good. But the more you consume, the marginal utility should be lower and lower, or higher and higher, or just remain constant. How do you think? The more you consume one thing, the marginal utility you derive from this consumption should be smaller, right? For most cases. So this one can be reasonable in most cases. Is a decreasing marginal utility. I like something, and the very first unit I consume, I feel, oh, so happy. And then the second, the third, and gradually I still think happier, but not that happier as the very first unit. Do you know what I'm talking about? Okay? So, we like to have a decreasing marginal utility. Then how can we do that? If we want to have a decreasing marginal utility, which means we just differentiate marginal utility with respect to Q1 should be negative, right? And this is the marginal utility. So this is actually, we just differentiate U utility with respect to Q1 twice. We differentiate once to have the marginal utility, and we differentiate twice to have the change in marginal utility. So now we differentiate again. We will have alpha minus 1, Q1 alpha minus 2, Q2 beta. Is that right? And if we wish this to be negative, we have already this property, alpha must be positive, is positive. And the only way to make this negative is to make it negative, right? To make alpha minus 1 negative. So alpha must be within this range. If alpha falls between 0 and 1, then what happened? Good one is a good, and which marginal utility is diminishing, is a decreasing or diminishing marginal utility. So same thing to beta. For good 2 to be good, more the better. Beta must be positive. But for the marginal utility of good 2 to be diminishing, then beta must be less than 1. Is that clear? Okay, so in the midterm, I just require you, or I just ask you to find this. For good 1 and good 2 to be good rather than bad, you need to derive these two conditions, alpha and beta, to be positive. That's it. I did not ask you to prove the second thing, to derive the second thing. Okay? Alright, then let's go back to check. What about CES? What about CES for good 1 and good 2 to be good? So this is the marginal utility of what? This is the marginal utility of good 1, and this is the marginal utility of good 2. It's a positive term. No matter the power of this term, it must be positive. Positive. So whatever value rho is, the marginal utility must be positive. Okay? Oh, once again, if you don't quite remember this, we just derive it again. So differentiate u with respect to q1, we will have 1 over rho and q1 to the power of rho, q2 to the power of rho, and 1 over rho minus 1, and rho q1 to the power of rho minus 1. But they can be cancelled, right? So this must be positive. This must be positive. And what about if we want to have a diminishing marginal utility? What about this property? We just differentiate this term again with respect to q1. So let's deal with the first term first and hold the second term. And it will be 1 over rho minus 1. And q1 rho plus q2 rho minus 2. And rho q1 rho minus 1. And q1 rho minus 1. Plus. Okay, we have already dealt with the first term and hold the second term unchanged. And then we hold the first term here, q1 rho plus q2 rho, 1 over rho minus 1, and okay, rho minus 1, q1 rho minus 2. And we have the multiple of these two would be 1 minus rho over rho. So it would be 1 minus rho something. Q1 rho, Q2 rho. 1 over rho minus 2, and Q1 2 rho minus 2 plus or minus, we just turn this into 1 minus rho. So we give it a negative sign here, right? So it would be Q1 rho plus Q2 rho. 1 over rho minus 1. Q1 rho minus 2. And, okay, here. It would be 1 minus rho, we have, and Q1 to the power of rho, Q2 to the power of rho, 1 of rho, negative 2, negative 2, and Q1, 2 rho minus 2, rho minus 2, okay, rho minus 2. Then we will have Q1 rho minus Q1 rho, Q2 rho to the power of, because we have already taken out 1 over rho minus 1. So 1 over rho minus 2, so it's a power of 1 here. Is it clear from here to here? We just rearrange the terms. We take out the first, the second, and the third. And what left in the parentheses? For the first term, we have still a Q1 rho. And for the second term, we still have a parenthesis with power to the power of 1. Okay? Anything wrong? If nothing wrong, then what would be this? This would be, okay, 1 minus rho and blah blah blah. Q2, Q1 rho over rho minus 2. And what about the square parenthesis? This would be cancelled, and a negative Q2 to the power of rho, right? Alright, so what about 1 minus rho? Because rho is less than 1. So remember that. Rho must be less than 1. So 1 minus rho must be positive. Okay? And positive, positive, negative. So automatically, no matter whatever rho is, CES satisfies a positive marginal utility and a decreasing positive marginal utility. Okay? Is that clear? So we have a positive marginal utility, first order condition, or first order differentiation, and we have a negative second order differentiation. So the marginal utility is positive but diminishing as you consume more good one. Yes.
Is there any case that that don't have the relation, like money? If you get more money, just their marginal utility just stay the same?
Well, it depends on your assumption. It's actually it depends on how you assume a human being, the nature of a human being. The more money you earn, how do you think the value of extra $1? Okay? So if you are so poor, the very first, say, $10,000 is so valuable for you, right? But if you are a millionaire, so what about an extra $10,000? Yeah. I would not say it doesn't matter. It matters, but does not matter that much as you were poor. Okay? Any other questions? All right. So let's just recall the properties for Cope-Douglas and CES. For Cope-Douglas, you must learn how to derive the demand functions. And for Cope-Douglas, Q1 is a function of y and P1. And in Cope-Douglas utility function, the good must be a normal good and satisfying the law of demand, but the relationship between good 1 and good 2 are independent. They are neither substitutes nor complements. And if you want the good in a Cope-Douglas utility function to be good and with a diminishing marginal utility, you must raise Chen here. You must have these conditions, okay? So alpha greater than 0 guarantees the marginal utility to be positive. And alpha to be less than 1, guaranteeing what? Guaranteeing the marginal utility is diminishing. But in CES, you see Q1 is a normal good, satisfying the law of demand. And the relationship between good 1 and good 2 depends on the value of rho. So if rho is here, then these two goods are substitutes. If rho is less than 0, a negative, then they are complements. Okay? And also, the marginal utility here must be positive and diminishing. Automatically hold. So we have already checked this. Okay? Any question here? So quantity demanded of each good is a function of the price of both goods and income. Oh, wow. How weird the demand curve is. Its price P1 is quantity demanded Q1. So what kind of utility function can make us to derive this demand function? This is the utility function form. So it's a perfect substitute. Okay? All right, given this functional form, Q1 plus Q2. So you know the indifference curves look like with a slope of -1, right? With a slope of -1. Is that clear? Okay. Now, let's have a look in 3 cases for the budget line. First case, the second case, and the third case. So the MRT, absolute value of MRT, what is MRT? MRT is actually P1 over P2, right? Do you remember this? Okay. So intuitively, let's have a look at this. Given our income, we may consume more Q2 than Q1. The quantity we may consume more Q2, right? So which price is cheaper or is less? Which good is cheaper? Good 1 or good 2? Good 2 is cheaper, so that we may buy more, right? Okay. So in this case, just like this. Oh, sorry. So P1 over P2 is greater than 1, which means P1 is greater than P2. So P2, good 2 is cheaper. In this case, P1 equals P2. In this case, P1 is less than P2. So we may buy a lot good 1, but just only a certain amount of Q2. Okay? So, what do you think? In the very first case, with this preference, this taste, our indifference curve look like this. So, what would be the optimal choice for us given this budget constraint? We will consume at this point, or this point, or this point. This one, right? It's a corner solution. Do you remember corner solution? I told you, corner solution. Okay? And what about the third case? When P1 is cheaper. So we will just push the indifference curve as outward as we can, right? So the final consumption bundle will fall on the horizontal axis, right? It's also a corner solution. But what about this? So we just push as outward as we can the indifference curve, and we find all points on the budget constraint, budget line, can give us the same level of utility, right? All right. So, in the very first case, when this height, let's denote it as P2. So would you please make a circle here? You just circle P2. So this value given it be P2. As P1, this is P1. As P1 is higher than P2, as P1 is higher than P2, just like what? Just like the first case. As P1 is higher than P2, so we spend all money on good 2, right? Not $1 on good 1. We spend 0 on good 1. So we buy none of good 1, okay? So you will see when the price of P1 is higher than P2, then the quantity demanded for Q1 would be 0. So that's the reason why we have a vertical blue line here. Because good 1 and good 2 are perfect substitutes, right? And now since P1 is more expensive, so why bother we should buy any Q1? We just spend all money on good 2, is that right? So 0 would be the solution. Okay? And what about this? What about this? Which means when P1 is lower than, or P1 is smaller than P2, this is P2. When P1 in this range is smaller than P2, which means P1 is cheaper than, good 1 is cheaper than good 2, right? So we spend all money on good 1 or good 2? On good 1, right? So since we spend all money on good 1, and the quantity we may have would be y over P1, is that right? Since we spend all money on good 1, and this would be the quantity we may buy, we may consume, okay? So this curve is actually a part of parabola, okay? 双曲线. But only within this range of P1, as P1 is lower than P2. So we may have this. So would you please put something here, saying Q1 equals y over P1. So this would be y over P1. Okay? As P1 falls below P2, then this curve, y over P1. And here, would you please just say Q equals 0. And the last one, when P1 precisely equals P2, when P1 equals P2 precisely, exactly, then from here to here, which means whatever Q1 on the budget line is fine. Okay, whatever you want. Either from 0 to here. And here, what would be the intercept? What would be the intercept? It would be y over P1. But now P1 equals P2. So it is y over P2. So y over P1 or y over P2. But here we don't say y over P1 because P1 is a variable. It can vary. It varies from 0 to an extreme high value, right? So P1 can be changed. Now we just fix P2 here. We fix a P2. So P2 is a fixed value. P2 is a fixed value. And as P1 equals P2, then this amount y over P1 should be y over P2, right? Understand what I'm talking about? So this is actually, would you please make a circle here, is y over P2. The reason is because it should be y over P1, but now P1 equals P2. And since P2 is a fixed value, so this intercept is also y over P2. And it is more precise. The reason why it is more precise because this value doesn't change, right? But if you just put down y over P1, then you know y over P1. P1 is now a variable which varies a lot from 0 to infinity, right? So if you put in this way, it is an